Howdy everyone, this is Team ML Project Warriors. Today I'll be showcasing our project which is integrating LSTM-CNN models for caloric prediction, a multimodal approach. I'm Tejas and here I have my teammates Hitarth Chopra and Rishabh Pagaria. Starting off with the abstract, the multimodal deep learning integrates diverse data types for complex problem solving and explores novel approach to estimate lunch calorie intake. As I said, we will be using diverse data types. So this data type, the data is of food images, CGM data, demographic information, microbiome profiles, and breakfast nutritional data. And as I said, we'll be using multiple models, but each model processes a certain type of data only. In our case, CNN takes care of the image data, and LSTM takes care of the time series data. The architecture of how we achieved our multimodal approach was firstly, there is a unimodal encoders which processes each modality independently. So as I said, CNN processes image data and LSTM processes time series data. So these are both unimodal encoders. And then the outputs of both these models is fused together in the fusion network, which integrates them. And finally, the fully connected layer makes a final caloric estimation. This helps us achieve our goal of developing comprehensive and accurate model predictions. The dataset that we used in this report is a nutrition dataset which contains breakfast and lunch information, data on motion, and photographs of meals across over 40 participants and up to 10 days. The dataset can be divided as follows. Firstly is the time series data, and as I mentioned, this was used by LSTM, the food imaging data used by CNN, the participants' demographics and microbiome data. This was not used, and why this was not used would be elaborated in the slides that follow. Other than that, there is labels for nutritional intakes, and this contains training predictions for lunch calories. And lunch calories is our target variable here.
So I'll be presenting our multimodal deep learning approach, which is used to estimate lunch calorie intake. So our project integrates diverse data types including food images, continuous glucose monitoring data, demographic information, microbiome profiles, and breakfast nutritional data. Here, the model architecture consists of three key components: unimodal encoders that process individual data types, a fusion network that combines these inputs, and a decision network for final predictions. So basically the main advantage of our approach include simplified pre-processing due to minimal missing values, and also the enhanced model robustness through focus on CGM and image data. Literature review. So we have plethora of sources were consulted when making this project and arriving at CNN and RNN as model choices and other decision for this project. These sources also provided valuable insights into the strengths and application of both convolution network and recurrent neural networks. So here are some of the key references for the multimodal deep learning approach are given below. Now let's talk about data processing. So the pre-processing steps are were really crucial for the multimodal for our multimodal architecture to effectively combine CGM time series data with image features for accurate calorie prediction. So let's talk about first how we have handled missing values. So for missing values, we replaced absent images with zero arrays and ensured that CGM sequences are properly formatted. Numerical data were normalized with image pixels scaled to 0, 1 range, and CGM values were standardized. We also implemented consistent padding across modalities with CGM sequences padded to 28 timestamps and images resized to 64 into 64 dimensions. And at the last, we also did data type conversion to ensure compatibility across all inputs. Now in our next slide, let's talk about the LSTM architecture. So the LSTM component was specially specialized for processing CGM time series data in our model. So it featured key components including memory cells, input gates, forget gates, and output gates. Here the architecture like uh, took the processed CGM data with shape 98,1 as input, which processes it through as an LSTM layer with ReLU activation, which was followed by the dense layer and dropout for regularization. This structure effectively captures temporal dependency in glucose monitoring data.
Now I'll be discussing the CNN model. The purpose was to extract meaningful features from breakfast and lunch images for classification and analysis. The CNN model, as depicted by the image here, can be divided into five layers. The first one being the input layer, which accepts images of shape 64, 64, 3. And then we have the convolution layers, which can be divided into convolution 2D layer and max pooling layer. And firstly, the convolution 2D layer takes 32 filters with 3 by 3 kernel and ReLU activation, and max pooling takes 2 by 2 pooling to reduce dimensions. And then convolution 2D layer takes in 64 filters with 3 by 3 kernel and ReLU activation, and then max pooling again does 2 by 2 pooling. And then we have the flatten layer, which converts 2D features, 2D feature maps to 1D feature vector, and then that is followed by dense layer, which has 128 neurons with ReLU activation for high level reasoning. And then finally there's the dropout layer, which with a dropout rate of 50% to prevent overfitting. This spits out dual encoders, one of them being breakfast encoder, another one being lunch encoder. And each encoder returns its tensor, input tensor, and the output of the last layer.
Fused model. So the fusion layer basically approach combines outputs from both LSTM and CNN encoders. The LSTM processes CGM data while dual CNN encoders handle breakfast and lunch images. These outputs were then concatenated in fusion layer, creating a unified representation that captures both temporal and spatial features. Hence, this combined representation then flows through fully connected layers for final calorie prediction. So for the like hyperparameter optimization, we use like these were the parameters which we use like LSTM units as 64, 128 for featured extraction, then CNN filters that is like 6496 for spatial feature processing, dense units dense units for fusion network capacity, learning rate that was like we kept it as fixed to 0.001 for stable training, and the dropout rate that is 0.3 comma 0.4 for regularization. So basically this parameter search space optimization ensured us the effective combination of temporal CGM patterns with spatial food image features. Now let's talk about the results. So our model showed significant improvement in early epochs, with training loss decreasing by half by the second epoch. And also, the performance was stabilized around the sixth epoch, achieving final metrics of 0.3123 training loss and 0.34 training RMSRE. And also, the validation performance was also comparable with 0.311 loss and 0.37 RMSERE, which basically indicates good generalization without overfitting. Thank you.